Hello everyone, this is DG Structures. This is a video on determinate structures and indeterminate structures. So let's get into it, everyone. Determinate structures and indeterminate structures. Before it is so key that we talk about this because it's more like a foundation. We usually check for the structure's determinacy before we go ahead to compute, the shear force and bending moment diagrams. So it is a key aspect of structural analysis. So let's get into it. Now, determinate structures, indeterminate structures. Now, to start with, a determinate structure is basically a structure, let's say for beam, for instance, that can be in equilibrium under the action of three reactions from the supports. What do I mean? Let's say this is my beam. Now, let's say I have a ruler here, and I have an hinge here. Now, of course, an hinge has just 1 degree of freedom, that it provides restraints in 2 directions. Let's assume 2 arbitrary directions. That is, if this is B, this is A, so BY, BX. This is L, length of the beam. Now, a roller support has 2 degrees of freedoms. That is, it has 1 restraint, AY. So you can see that this structure is in equilibrium under the action of 3 support reaction forces. Now, what if the structure still remains at equilibrium but under multiple reaction forces? Or before I even go into that, you must understand something also. Why we call it statically determinate. We also call it statically determinate because we have, firstly, we have some things called the equilibrium equations. Equilibrium equations from statics. Equilibrium equations. These are important equations. For a 2-dimensional, that is a plane structure, we're just going to be considering 3 of those. That is summation Fy equals to 0. Let's say positive. Summation Fx equals to 0. Let's say positive. And let's give it a counter moment, positive. M, about a point, is equal to 0. Of course, let's say Mz. It will be Mz. For those that have used softwares like Portal Structure, you understand what I mean. Like Start Pro, you understand what I mean. So I gave it Mz because see something. You remember that it's a let me give you this. Remember that it's a 2-dimensional structure we're dealing with. So I remember that we have a coordinate system in this manner, an axis in this manner. We have the y-axis, we have the x-axis, and we have the one that is pointing out that is coming to meet you from the screen, which is here, Z. So when we have a moment rotating about this axis, we call it Mz. Basically, this moment is the moment you can see from the screen. It's just like having something like this. So that is why we call it Mz. Had it been it was mx, it will create torsion on our two-dimensional structure. I hope we understand, but we'll go into that later. The point of the video is to tell us that statically determinate structures are those structures in which the reactions can be computed with the equilibrium equations. I mean, there are three equilibrium equations. So it means that for us to solve a statically determinate beam, the beam must have three unknowns. Three unknowns. It's not that, okay, of course there are some simultaneous equations where or normal equations where you have two equations and you have two unknowns. You have two unknowns and you have three equations. Fine, you can solve that. You can solve for those unknowns using those three equations, but that is not what statically determinate structure is all about. Statically determinate structure needs three unknowns. Which can be gotten with three equations. That is the beautiful thing about it. Now, there's something that we need to know even before I go to statically indeterminate, or let me go to statically indeterminate structure because I've started it already. So let me go to statically indeterminate structures. Statically, why on the other hand, statically indeterminate structures indeterminate. Those are the structures that needs more than three external reaction forces in order to keep itself in equilibrium. In essence, what this is talking about is that it has extra unknowns. That is, we can't use, I mean, if something has 5 unknowns, and we have unknowns, and we have 3 equations, we can't solve this. I mean, we have just 3 equations. We can't solve for something of 5 unknowns with 3 equations. The difference, which is 2, is called the degree of indeterminacy. Now, let's say, let me give you also an example. Let's say we have a structure in this manner. One end fixed A, and this manner, hinge support. So here we have 3 reactions assumed arbitrarily. This also 2 reactions as restraint. So how many? We have 5 unknowns. But once again, we have 3 equations. There's no way we can solve this directly. So we have to use either the force method or the displacement methods. Methods which involves moment distribution, which involves slope deflection. Or we have to use the modern metrics. So now I want to now build on this foundation. There's something called an internally, or there's something called a rigid structure. A rigid structure are the structures. Let's say I have this, and it is supported. A rigid rigid structure is the structure that when you remove the reactions, that is the support rather, when you remove the support, the structure undergoes a slight deformation, or rather a slight displacement. That is, it is still safe, it is still standing, it is not wiggling, it can't wiggle, it will still stay the same manner. Okay, if I remove these two supports and the structure still remains like this in this manner, it means that this structure is an internally stable structure, also called a rigid structure. Also called a rigid structure. Sorry about that. On the other hand, there's something called an internally unstable structure. Unstable structure. An internally unstable structure. Now, an internally unstable structure, let's think of something like this. I'm aware that we've heard about internal hinges. They are just basically models used to basically represent that moment can't be transferred at that particular location, although forces can be transferred. We just use internal hinges to model that, engineering behavior. So this is, let's say we talk about this. Let's give it a roller support. We're just assuming. Let's give it something. So a roller support, for instance. Okay. So this structure, if I remove the support, I would have something like this. Remember that internal hinges can't resist rotation. Remember that internal hinges can't resist rotation. So eventually there will be a displacement compared to its original, and it will be significant. It can even drop. So this is considered an internally unstable structure. Sorry. Unstable structure. Now that we've identified that we have internally unstable, internally unstable. Now that we've realized that we have internally stable, now we've established these two guys. So let's now move back to what we did in the beginning of the video, whether it is determinate or indeterminate. Now that the first thing when you see structure, the first thing is to identify whether it is an internally stable structure or an internally unstable structure. Regardless of its kind, you can now further classify it into being determinate, statically determinate externally, and indeterminate externally. Now, I'm using externally to denote that they are basically external influences, support. Remember that when we have a structure, let's say this is it. It's the support that we are looking out for to know whether it is determinate or indeterminate. For instance, we have here two reactions. So because of this support, which are external agents, we have three unknowns. So all these basically are external. So that is why we are classifying it as indeterminate externally or determinate externally. Once again, the first thing you do is to know whether the structure is internally unstable or stable. Then whether it is unstable or stable, you can now further classify it into being indeterminate externally or statically determinate externally. So if it is internally unstable, it can also be statically indeterminate externally and statically determinate externally. So let's now look at a rigid. Let me now build on it one by one. Rigid or internally stable structures are the ones that will not have significant deformation or displacement when support is removed or detached. Structures. Internally stable structures. So now let's look at determinate. Once again, I'm like determinate externally. Statically, of course. Externally. It's still the same concept with what I did as above. Just for understanding's sake. So this is a rigid structure. Once again, it does not have an internal hinge. It does not have an internal roller. So it is a rigid structure. And so this is this. This is this. Now this structure, of course, is determinate. Now, what of this? What of this? 1, 2, 3. This is a statically determinate, that is externally, of course, it's a rigid structure, but it is a mechanism in the sense that it is geometrically unstable. Now, apart from all these two, there's also something called unstable structures. Unstable structures. Unstable externally. Oh no. Structures. And statically determinate, of course, unstable also is part. Now, I would move here. An unstable structure, an unstable externally structure is basically, depending, of course, on whether it can be internally stable or unstable, it doesn't matter. We can still classify any of them as indeterminate, determinate, or unstable. Now, an unstable structure is basically the structure that just has, let's say, a structure like this. It has two reactions, for instance. So, of course, two reactions, two unknowns. But we have 3D equations. Fine, equilibrium equation can work to solve this. However, we cannot use this kind of structure in our designs. we cannot use this type of structure with this condition of constraints as per the support in our designs. Why? Because it is considered an unstable structure externally. Once again, externally, because of the support conditions. Unstable structure and externally. Now, apart from a structure, whether being stable or internally stable or unstable, now you can see that an internally, for this case, an internally stable structure for this particular being and structure, it's considered, it can be considered unstable because of what just happened, the two unknowns and everything. Also, you should also know that it is also possible an internally unstable structure can be unstable externally also. So, knowing this, we can now continue with what we're doing. So, statically determinate externally for rigid structures. Now, we've identified that this is a statically determinate structure. This also is a statically determinate structure. However, it is a mechanism. It is geometrically unstable, which is something we need to look out for. To avoid geometrically instability, we need to ensure that the forces that the reactions provide are not parallel. The forces must not be parallel. They must not be parallel in order to ensure that the structure is geometrically stable. For this particular structure, they are all parallel, the forces. So we can consider it a geometrically unstable structure. Another scenario for it not to be a geometrically unstable structure is that they must not be concurrent. Current. Hey, help me. Spelling. Okay, I guess it's this way. Concurrent. Concurrent forces are basically forces that will basically meet at some point. Let's say this. They all meet. An example, this can be modeled in this manner. Let's say we have a support in this way. Let me go further. Yes. Okay. Now, let's say we have something like this that will meet, that is the force is extending here. And we have another one, so in this direction. Remember, when you have a roller orientated, the applied external force induced, the applied external force due to the restraint, as per it's a roller, would also be orientated. Similarly, for this, let's say it's orientated in this manner, or even if it is sitting normally, it can still intersect. Mistake. Can still intersect. Can you see? And we consider it a geometrically unstable structure. So for it not to be considered a geometrically unstable structure, it must not be parallel and it must not be concurrent. So this is determinate, although it is geometrically unstable, so it cannot be used. We cannot proceed with analysis. Now, of course, we can now move to the internally unstable structures. Unstable structures, but it is statically indeterminate. externally. Now, statically indeterminate externally. Let's say we have a beam and we have an inch. Let me do determinate externally first. Let me do determinate externally. Now, for let's say this structure has an inch here, and let's say this is a fixed support. Sorry. This is a fixed support. And let's say this is an inch support. Now, ordinarily, when we look at this structure, 1, 2, 3 support reactions. 1, 2. It has 5 unknowns. Or let's make it have just 4 unknowns. Let's say this is our structure. So it has 4 unknowns. 4 unknowns. Now, for this particular structure, remember it is internally unstable. That is why we're having internal hinge, the first foundation. So it has 4 unknowns. Now, equilibrium equation is just 3. 3 equations. However, you might be thinking that, yes, mathematically you can't solve 3 equation. You can't solve for those 4 unknowns with 3 equation. It is not possible. So you might be thinking that this structure is indeterminate. However, I tell you that the structure is not indeterminate. It is determinate because we can have one equation. We can have one more equation that can combine with this 3 equilibrium equation plus 1 equation. Where does this 1 equation come from? That 1 equation comes from this influence. So it means that we have 3 equilibrium equation and we have this 1 more equation that came from our structure. So we have 4 equations. Yes, so we can now say 4 equations can solve 4 unknowns. Now we can now consider it to be a determinate structure externally, a statically determinate. Externally, we can consider it. Yes. This 1 more equation that came is something called an equation of condition. Of condition. We'll talk about it later on, but please keep it down somewhere. Now, let's move to internally unstable structures, but they are statically indeterminate externally. Let's look at this. The same structure, but a different stuff. Let's say we have an internal hinge also. So, 3 equations. So, with the separation, we're dealing with indeterminate now. So, indeterminate, but still under internally unstable structures as per the internal hinge. So, dealing with these, we can say that we have 5 unknowns. However, we have how many equations? 3 equilibrium equations plus one equation of condition or construction. They call it either equation of condition or equation of condition. So it means that we have 4 equations to combat these 5 unknowns. So even with this extra equation, it does not, it can still solve for these 5 unknowns. So we can say that the beam is statically indeterminate externally. Statically indeterminate externally. It has a degree of indeterminacy of 1, because I mean just 1 left if you looked at the first thing in the video. Now let's move to the last one. Still under internally unstable structures, but now internally unstable structures but statically unstable externally. Internally unstable, statically unstable externally. Let's say we have this also. Now let's say we have this. So this means we have 3 equations. 3 equations. 3 unknowns. But we have 3 plus 1 equation. Remember, 1 is equation of condition. So we have 4 equations. So remember, I mean, we can solve this structure. We can solve for the unknowns because we have an extra equation. We have more than enough. So that makes it unstable. It is not statically determinate. You remember I said it. It makes it unstable externally. So we can consider this internally unstable structure as an unstable structure externally. Thank you. Now, we have something also called internal rulers. Internal rulers. This is internal hinge. All these internal hinges, internal rulers are under internally unstable structures. I'm not deviating. So I'm going back to wherever I have my internal hinge. I want to do a separate one for internal rulers. For internal rulers, I will model it this way. Let me erase this. Let me put this. Let's say I have this structure. Now, this structure has 3 plus mistake, sorry. This structure has 5 unknowns. Remember, it's under statically, it's under internally unstable structures because of this internally stuffs. Internal hinges, all those ones that are under internally unstable. So it has 5 unknowns. But But how many equations? Let's see. It has 3 equilibrium equations. Equilibrium equations. Plus, remember, internal hinges provides 1 more equation, but internal rollers provide 2 equations. 2 equations. So making 5 equations. Once again, equation of condition. Five equations. So we have 5 equations to combat 5 unknowns. So it is statically determinate externally. That is, this internally unstable structure is statically determinate externally. So the same process is repeated. It's just that this time we're having 2 what's the name? Extra equations, not 1, unlike the internal hinges. It's still the same pattern. Thank you so much.